When we first learn about turn, a measure of turn, we usually think in terms of a full turn or a half turn. And if you ask somebody to turn a quarter turn or to twist an oven knob a quarter turn, they understand what you're talking about. When we want to get a bit more precision, we break that into pieces. The natural way of breaking something into pieces before the metric system came along was to choose a number that divides by lots of things. 360 has 24 different factors. It's built from 2 times 2 times 2 times 3 times 3 times 5. So it was a logical choice. You can break it into fifths or 20ths or 15ths and all sorts of other fractions. But the more maths you start to do, the more you realize that 360 is a fairly arbitrary choice when it comes to doing real trigonometry, especially when you want to do trigonometry with calculus. As a case in point, this question asks you for the angle in the sector, and it looks like a fairly nice section of a circle. The two radii are shown, and the arc length is also shown. That happens to be the same as the radius, exactly 1 centimeter. If you were to find the exact form of the angle, it comes out looking a bit weird, 180 divided by pi degrees. That comes from the fact that the circumference of the circle is itself going to be 2 pi times the radius, in this case 2 pi times 1. And we want to go just far enough around to have 1 out of the 2 pi of that circumference. Since the number of degrees is always going to be 360 for a full turn, a fraction of a full turn will be some proportion of 360 degrees. It gets stranger when we start looking at the area of the sector. In this case, we take our number of degrees and we look at that as a proportion of 360, and that gives us the proportion of the entire circle, and the pi disappears. It's almost as if the pi was an inherent part of how the circle works, and by using degrees we've completely ignored that, and therefore we have to adjust for the pi. We have to multiply by 180, we have to divide by pi just in order to get something which tells us what we want to know. It comes out as an awkward looking number. It's about 57.3 degrees, but it's not even a rational number. It's 180 over pi. Now, instead of measuring things in degrees, the alternative is to measure things in radiuses, or as it's more usually called, in radians. We want to measure how many radiuses of arc we have turned. If you turn far enough to make a sector of the sort that's shown on the screen, you've turned exactly 1 radian. If all of those ones had been 20s, then it would still be 1 radian, just be a scaled up version of the same diagram. So there's no particularly good reason to stick with 360. The question is it really worth changing over to such an awkward number as 2 pi? Well, there's a few things that I can probably do to convince you that it's a good idea. The first one is to look at the graph of y equals sine x. Now, usually when you see a graph of y equals sine x, you don't see it drawn to scale. The graph at the top is the standard graph that we teach to 14-year-olds, and it shows the graph of y equals sine x for values of x from 0 to 360. The difference is we've drawn it to scale, so the x and y axes are now scaled appropriately, and it's clear that this particular sine wave doesn't look much like anything. It doesn't go very high, it doesn't go very low. It might make more sense if we're going to have one archetypal sine wave that we work with to have one that behaves a bit more sensibly. The one at the bottom is also measured to scale, but that one is measured in radians. So instead of measuring how many degrees we go around a circle, we measure how many radiuses we go around the circle. And it turns out that's a much more natural measurement to use. There's all sorts of things that you might spot when you look at this curve. A few sensible questions to ask yourself will be, how steep is the graph? There's no particularly pleasant answers for that for the first graph at the top. But for this graph, it starts out, as it turns out, with a gradient of exactly 1. And it tails off to 0, and then becomes more and more negative until it gets to exactly -1. The gradient of -1 happens when x equals pi, and then it comes back to a 0, and then back to a +1 again. The area is another interesting one. you can probably estimate the area reasonably well. In fact, you could approximate the area bounded by the curve and the x-axis between 0 and pi by a triangle with a height of 1 and a base of 3-ish. Well, that will give you an answer about 1.5. That will be an underestimate because the curve is concave between those 2 points. In other words, it bows outwards and the triangle would undercut the curve. Well, it turns out the area is exactly 2. So if you go from 0 to a half pi, you've got an area of 1. If you go from half pi to pi, you've got an area of another 1. If you take the next section from pi to 2 pi, you have an area of -2, or 2 units of area below the x-axis. So if radians make more sense for the graph, and radians make more sense when we're talking about the area under the curve or the gradient of the curve, then it seems like there's sufficient motivation to work with them. We'll avoid having lots of awkward multiplying by 180 and dividing by pi things going on. So initially, the thing to get your head around is that radians are just a measure of turn. Why we use them is that they work when we're doing calculus. There are a couple of things that's useful to get to grips with at this point, and the more familiar you get with them, the easier you'll find calculus with trigonometry. Firstly, converting between degrees and radians and getting a feel for what kind of numbers you would expect. For all of the nice fractional amounts of turn that we've come to recognize as 90 degrees, 60 degrees, and so on, we can convert them into something which is much more logically like a fraction of a turn. Technically, it's now a fraction of a half turn because pi radians is the same as 180 degrees. It will be a complete reversal of direction. So when we have pi by 6, it's a sixth of a half turn, which is equivalent to a 12th of a full turn. We say those as pi by 6 or 3 pi by 4, etc. And that tends to be how they're quoted as multiples of pi, because all of those nice angles are nice multiples of pi, nice fractional values related to pi. In fact, once we've accepted that we're going to have fractions in there, we can end up with pi by 7, 7 pi by 9, and all sorts of other awkward things that wouldn't necessarily work with 360 degrees. The other thing that's worth noticing is that the approximations in radians are worth being approximately aware of. So 1.57 is one that might stick in your head for a half of pi. If you know that pi is 3 and a bit, that's good enough to recognize that 2 pi will be 6 and a bit, and it will help you to spot when you've gone beyond the range that a question needs you to. Now, the other really nice thing about radians that you can get as an advantage straight away is that the results that we've previously calculated for arc length and sector area, which were messy and involved dividing by the number of degrees in a full turn and then multiplying by either 2 pi r or pi r squared. Well, if we use radians, we're not dividing by 360 degrees anymore. We're dividing by 2 pi radians, which means the pi cancels out in both of those equations. For the arc length, we get L equals r times theta. That's it. It makes sense. R is the radius of the circle and theta is the number of radiuses we go around the circle. Well, if you have a radius of 10 and you go 3 radiuses around the circle, you'll have an arc length of 30. That's what 3 radiuses is. So that one is very much bound up in the definition of a radian. For the arc length, half r squared theta may look a little strange. It should be obvious that that is an area while the arc length is a length. Because we have an r squared, you're squaring a length, you're squaring the radius, which is measured in centimeters or meters. It's worth noticing at this point that theta itself doesn't have any units. I know we've been banging on about radians, and you might be thinking, well, surely the units are radians, but technically radians are dimensionless. So you could argue they are units, but they're not physical dimensions. In other words, you can multiply by a number of radians and not affect the dimensions of the quantity you're talking about. You can multiply a distance by radians and get a bigger or smaller distance. You can multiply an area by radians and get a bigger or smaller area. In that sense, it's a lot like multiplying something by pi or by a half. You can scale it, but you can't change the essence of what it is. The last one here, the segment, it's not usually worth memorizing a bespoke formula for this one. We can get the area of the sector, the entire shape, which is represented in the middle section here, and then you can subtract from that the area of the triangle. Usually half AB sine C is a good choice for the area of the triangle here, because although you wouldn't necessarily know the height, you would generally know the radius, which is the A and the B, and you would usually know the angle, or at least you're interested in it because it's going to appear in the formula for the sector. There's a couple more things that might be worth recalling to your attention. The two famous triangles, an equilateral triangle cut in half and a square cut in half, these two triangles are used to determine the exact values of various trig identity ratios: cos 30, cos 60, sine 30, sine 60, sine 45, cos 45, and tan of 30, 60, and 45 as well. You can get those in 30, 60, and 45, but there's nothing to stop you from writing these angles in terms of radians. So for instance, your 30-degree angle at the top of the bisected equilateral triangle is pi by 6. The angle at the base will be pi by 3, that's 60 degrees. And then in the isosceles right angle triangle, both of the angles are pi by 4. So we can calculate and start to recognize, just like you recognize that sine 30 is a half, you'll start to remember that sine of pi by 6 is a half, and gradually this will become more like your native language for speaking about angles when we do pure maths. The next part, this is a quick recap of how we deal with trigonometric equations. The first thing to notice is that you will have a solution range, and the reason this is important is that there are many possible solutions. If a trig equation has solutions, usually it has an infinite number of them, depending on the complexity of the situation. So for instance, if sine 2x is a half, it could well be that x itself was pi by 12, 15 degrees, because then two lots of it would be pi by 6, or 30 degrees, and sine of 30 degrees, or sine of pi by 6, is a half. However, there's nothing to stop it being something different. You could go forwards and backwards as far as you like. The first thing will be to use the symmetry of the graph, or the symmetry of the unit circle, to determine that the next angle will be just a little shy of a half turn. In other words, just off 180 degrees, or just off pi radians. So here is our 30 degrees and our 150 degrees converted into radians, pi by 6 and 5 pi by 6. Now, the original range we were given was between 0 and 2 pi. You might notice, if you're good with fractions, that I've calculated values of 2x that go from 0 up beyond 2 pi, up towards 4 pi in fact. The reason for that is that I'm about to divide them all by 2. And that means that effectively the range I need to consider when I think about an ordinary inverse sine and the additional solutions from a sine graph, they need to be solutions for 2x, and they need to cover twice the range. For cos minus cos squared, very common mistake here is to divide both sides of the equation by cos x. If you do that, you lose an entire set of solutions. There are two ways this equation can be satisfied. One of them is for 1 minus cos x to be 0, certainly, but the other one is for cos x itself to be 0. If cos x is 0, we get two solutions, pi by 2 and 3 pi by 2. That's your 90 degrees and your 270 degrees. And if cos of x equals 1, in other words, if 1 minus cos x is 0, then we get an additional solution, x equals 0. You might be wondering where the 2 pi has gone from here. That comes from the inequality in this range. So you need to look very closely at each end, at any extremes, the edge cases. In this case, we do want to include 0, but even if 2 pi satisfies the equation, it's not within our range. So we don't include that value. For the third part, sin x equals tan x, a similar thing can happen here. Once you rearrange into a form where you can solve, you'll find that sin x is a factor of both sides, but don't be tempted to divide by it. Subtract sin x from both sides, take out sin x as a common factor, and you will generate solutions from sin x equals 0. In this case, most of the solutions come from that one. You'll notice here, although technically there are 3 solutions we've found, one of them is a duplicate. So we've made this bracket 0 and we've made this other factor 0, but there are some values of x for which they're both 0 simultaneously. Next, we have a quadratic graph that goes through the points root 2, minus root 2, and 1. To find the equation of a graph like this, you would need to first consider the roots. We can generate for ourselves a quadratic that has the correct roots, and then we can find ways of transforming it so that it perfectly matches the situation we have here. So the first thing I would say is, if it has a root at root 2, it has a factor of x minus root 2. Similarly, we can get another factor, x plus root 2, because of the other root, negative root 2. However, if you expand this out and you consider what the graph of y equals x squared minus 2 would look like, you realize that it does not go through the point 0, 1. In fact, it doesn't even look like this. It's curved in a completely different way. However, every single quadratic that goes through the points root 2 and minus root 2 is just a vertical stretch away from any other quadratic that goes through those 2 points. If it shares the same roots, you could stretch it or squash it vertically and convert it into another quadratic with those roots. In this case, we just need to multiply the entire quadratic by negative 2. If we do that, that will allow us to generate a quadratic that has a maximum point at 0, 1, rather than a minimum point at 0, negative 2. So that gives us this weird looking quadratic, 1 minus x squared over 2. What this has to do with trigonometry, you're going to start to discover soon. This graph in green crosses not at root 2, but at approximately 1.57. which you might recognize from before as half pi. This graph here, in fact, is cos x. So we have a quadratic on the inside, and we have y equals cos x on the outside. Remarkably similar, provided the value of x, the angle, is fairly small. What do we mean by fairly small? Well, in this case, you can see the larger the value of x gets, the more discrepancy we find between the quadratic and the trig graph. But for pretty much any value below 0.5, and remember this is 0.5 radians, so if a radian is approximately 60 degrees or slightly under, then half a radian is going to be 30 degrees. We've got a fair amount of flexibility here. Between plus and minus 30 degrees, there's very little difference between cos of the angle and 1 minus the angle squared over 2, provided the angle is measured in radians. So you can try cos of 0.3, and try 1 minus 0.3 squared over 2, and you will find that those two give very similar results. If you're curious about this 1 minus x squared over 2 and why it should match cos x, that's a topic we're going to get into in more detail when we do further maths. But for those of you who are too impatient to find out what the expansion looks like, there is something called the Taylor series, which is equivalent to the binomial expansion for things which are not binomials. Essentially, we have an infinite polynomial which corresponds to cos x, and it is increasingly accurate as a representative of cos x, provided x is small enough. And what we're seeing here is that if x is very small, in other words between approximately plus and minus 0.3, 0.4, then even the first two terms give a very good approximation for the value of cos x. Here's a few more. You'll notice that if you zoom in on the sine graph, very close to x equals 0, you find that it looks a lot like a straight line. In fact, that's one of the simplest ones we can look at. The tan graph does a similar thing. You can't see the tan graph on here, but if you were to draw the tan graph, because tan is sine over cos, sine is 0 when x is 0, and cos is 1 when x is 0. So tan is 0 when x is 0, but not only that, because sine is increasing linearly and cos, close to 0, is not changing very much, tan itself, roughly, is increasing linearly. It diverges from the line by going above it rather than below it, like sine does, but it starts out initially with a very similar approximation. These are known as the small angle approximations. Sine of theta is roughly the same as theta. It's not just a straight line, this is the line y equals x. Has a gradient of 1, remember, when we're dealing in radians. cos 1 minus x squared over 2, the one we generated, and tan exactly the same. Tan of x will be equal to x, tan of theta will be equal to theta, more or less, provided theta is small enough. And again, this all works and only works if theta is measured in radians. We can use this kind of thing to get approximate solutions for equations that would otherwise be too difficult to solve. X plus sine x equals something, for instance.